Hello everyone, now we're on chapter 2 and your textbook names this chapter Chemistry Comes Alive. And it's absolutely essential that you understand some chemistry in order to understand how the human body works. I've split this chapter into 3 short lectures, and this first PowerPoint script will include parts A and part B. First of all, we're going to review a few little basic chemistry concepts. Matter is anything that has mass and occupies space. Matter occurs in the 3 states, solid, liquid, and gas, as you can see represented here. Solid water is ice, liquid water, and gaseous water, which is water vapor. Energy is the capacity to do work, and the major types of energy are kinetic energy, that is energy in action. Then there's also potential energy. Potential energy is stored or inactive energy, and energy can be transformed from potential energy into kinetic energy, and that's represented with this figure right here. The young man has a bow and arrow, and he is pulling, as he pulls back on the arrow with the bow, he's actually putting in some of his energy using his muscles, and having this pulled back like that is representing potential energy, because when he lets go of that arrow, the arrow will fly through the air, and that would be a form of kinetic energy. And he's going to shoot it right over into that target right there. Forms of energy include chemical energy, electrical energy, mechanical energy, and radiant or electromagnetic energy. And of course, the electromagnetic spectrum includes all the frequencies of energy coming to our Earth from the sun. Energy form conversions. You may remember with your from your Fundamentals of Biology class that energy may be converted from one form to another. However, some usable energy will always be lost to the environment as heat each time it's converted. And this is represented by looking at this food chain. You can see this progressive loss of energy, although this is actually loss of usable energy, in passing this energy up the food chain. So first of all, the sun is beating down on the earth. Much of that energy is going to be lost, air quotes, to the environment as heat. But there is a certain portion that's going to be captured by the producer level of organism, which include plants, blue-green algae, and other like cyanobacteria that will capture some of that sun's energy. Then when the deer comes along, or other kind of animal that eats the plant, only a certain part of that plant and the energy stored in that plant will be available to the deer to meet its energy needs. Some of that will be lost to the environment as heat, when actually, though, that's going to provide for the body heat of that animal. Now we have the lion come along, and he will feast upon the deer, and of course not all the energy that was captured by this deer in his diet will be available to the lion. And again, some of that energy is going to be converted into heat. Matter is composed of elements. Elements, remember, cannot be broken down into simpler substances by ordinary chemical methods, and each element has a unique property. And here is a representation of the elements in that periodic table of elements, which we will be talking about briefly. Now, each element is composed of one type of atom. So the name of the element is the same name as its atom. Atoms are the unique building blocks for an element. The atoms give the element its properties, and the atoms are the smallest particles of the element with its properties. And here's a representation of an atom. Remember, you've got your atomic nucleus in the middle. These are showing you some protons and neutrons, and then the electrons are spinning around that atomic nucleus at great speed. The atomic symbol is a 1 to 2 letter shorthand for each element. I thought this was pretty funny. Barium, Ba, cobalt, and nitrogen. They're actual symbols. Major elements of the human body. Even though there's many elements represented on the periodic table, only about 4 of them make up the human body. In fact, 4 of these elements make up 96.1% of your body mass. Over here on the left, you can see the name of the element, and over on the right, its corresponding atomic symbol. Carbon, C, hydrogen, H, oxygen, O, and nitrogen, N. The lesser elements of the human body include 9 additional elements that make up another 3.9% of body mass. So we have the elements listed here: calcium with the symbol, phosphorus, potassium, sulfur, sodium, chlorine, magnesium, iodine, and iron. Some of these atomic symbols were obtained from the Latin name for the element, so sometimes it doesn't look like it would be, for example, it's not the first letter of that English term. The trace elements of the human body, these are found in tiny amounts, but they're actually quite essential, and about 11 elements make up about less than, actually, 0.01% of body mass. Many of these are part of or activate enzymes. Here are those elements: chromium, the symbol, copper, fluorine, manganese, silicon, and zinc. Now we're going to go to atomic structure. The subatomic particles, protons, neutrons, and electrons, are represented right in this figure. There are, of course, subatomic particles such as gluons and quarks, where these particles will actually decompose to smaller particles, but we're not going to get into that. We're just going to concern ourselves with the protons, neutrons, and electrons. Protons and neutrons, of course, reside in the atomic nucleus. A proton will have an electromagnetic charge of plus 1. Okay, they have an electromagnetic charge. And neutrons are also in the nucleus, but they do not have an electrical charge. Electrons orbit the nucleus. Now, electrons they don't really have any weight at all. They have no mass virtually, but they do have an electromagnetic charge, and this is a negative charge. So these figure 2.1. These are representing some models of the structure of an atom, and this atom happens to be the helium atom. The atomic number is 2. The helium typically has 2 protons, and that's why they show the little p with the plus, because of the protons have a positive charge. 2 neutrons, which would be the yellow balls right there, they're neutral, and of course 2 electrons orbiting the atomic nucleus. This is the planetary model because it kind of looks like planets going around the sun in our solar system. This one is called the orbital model. So they show the protons and neutrons in the atomic nucleus, and down here it just shows you this is an electron cloud, because the electrons actually are not going in a circle around the atomic nucleus. They're actually spinning, in this case in a spherical manner, around the atomic nucleus. Okay, so to identify elements, we use the periodic table of the elements that has the atomic symbol, the atomic number, and the mass number. Different elements, of course, have different numbers of subatomic particles. The atomic symbol will be that letter. Here's nitrogen. This is an N, obviously. The atomic number up here in the upper right, that is the number of protons in the nucleus, which does not change. The number of electrons can change once these atoms start interacting with other atoms, but the number of protons will stay the same. Therefore, this is called the atomic number. The mass number is down here. This is also called the atomic weight. Now keep in mind, protons weigh 1 AMU. That's called an atomic mass unit. It's so tiny you can't weigh it on a scale, even a gram scale. And protons weigh 1, and neutrons also have weight. They also weigh 1 AMU. So when you see this this number, this is not a whole number, it's actually an average of all the samples of that particular element that have been obtained. So it's going to be not a whole number. And this is showing, of course, nitrogen, atomic number of 7. This is showing the atomic structure of the 3 smallest atoms. From the left, we have hydrogen. Hydrogen is number 1. Generally, all it is a proton and an electron. And this electron can take off and start interacting with other atoms. So it's a very, very powerful atom or element. Here's helium. Helium has 2 protons and typically 2 neutrons, and there's 2 electrons. We're going to be talking about these electron shells too. This is the first shell, and it can hold up to 2 electrons. Now we have the third element. This is lithium, and its atomic number is 3. There are 3 protons in the atomic nucleus. It typically has 4 neutrons, and in the neutral state we see it has 1, 2, 3 electrons. You may notice that the second circle is added. This is representing the second shell out, which actually you'll find pretty soon in the PowerPoint. We'll be talking about the octet rule. From here on out, each shell can contain up to 8 electrons. So first we're going to talk about isotopes. This is related to atomic weights or the mass of an atom. An isotope is a structural variation in an atom. The isotope will differ in the number of neutrons. The atomic numbers are the same, but these will have different mass because remember I mentioned that each neutron weighs 1 as well as each proton. And so if a particular sample of that element has an extra neutron or 2, it's going to have a different mass. So the average of the mass numbers, or the relative weights of all the isotopes of that atom, will end up to be the atomic weight. And again, there's nitrogen at 14.01 mass. So hydrogen is number 1 again, and this has different isotopes. So hydrogen always has 1 proton. That's what it is. That's its atomic number. And in the neutral state, it will have 1 electron. Typically, hydrogen does not have any neutrons. However, if there's a sample found that has a neutron in it, that's called deuterium. And now there's another type of isotope. It's called tritium, and that hydrogen atom would have 2 neutrons. Radioisotopes. The reason I like to talk about isotopes in anatomy and physiology because these are very important in medicine. Heavy isotopes, and heavies pretty much relating to the fact that there's extra neutrons in it, these particles will actually decompose. They break apart, and so that isotope will turn into the more stable form. When they break apart, these little pieces are given off as particles, and the particles can be picked up with radioactivity scanners. Over here you can see a Geiger counter, and then here is a machine that will actually pick up a radioisotope that, if it's been injected into that individual, as that isotope decomposes, those particles will be given off and can be picked up by these scanners. Something like a CT scan. That's called computerized axial tomography, CAT, and other X-rays will be able to pick up bony structures in the body, but also something like fluoroscopy as this radioisotope is emitting the particles. These machines that are highly sophisticated will pick them up and can create images. And again, you can see right here, there's an image. Radioisotopes are valuable tools for biological research and medicine, and they do have the same chemistry as their stable isotopes. Molecules, compounds, and mixtures. Most atoms chemically combine with other atoms to form molecules and compounds. And most matter actually exists as mixtures. This is when two or more components become physically intermixed. And there's three types of mixtures: solutions, colloids, and suspensions. With a solution, you will have a solvent and a solute. So the solvent is the substance present in the greatest amount, and it's usually a liquid. In living cells, the universal solvent is water. Obviously, water doesn't dissolve all things, but in living cells, water is the solvent. Solute, this is going to be present in smaller amounts, and it's the particles that are dissolved in the solvent. Colloids and suspensions. Colloids and suspensions are called heterogeneous because there's actually several things together that make up that material. The visible solutions can settle out of a suspension, but they cannot settle out of a colloid. So in the middle here we see jello cubes. That would be a colloid. And over on the right, you can see a whole blood that has actually been centrifuged so that the heavier particles can come out of this solution into the bottom of the test tube. Milk, this is milk. Milk actually, when it's fresh, is a type of suspension, or at least the milk fat will come up to the top. But typically what we drink is called homogenized milk, so that it's more like a colloid. Here's another figure that illustrates that. On the right, you have a solution. So solute particles are very tiny. They do not settle out or scatter light. The example here is mineral water, or something like a saline solution where the particles are actually dissolved in the liquid. Here is a colloid, and there's jello again. The solute particles are larger than in a solution, and they do scatter light, and they do not settle out. And on the far right, you can see that example again of the blood. The solute particles are very large, they settle out, and they may scatter light. So blood is actually a suspension. It has the liquid plasma, and there are also ions like sodium chloride that are dissolved in it, but it's considered a suspension because when you take whole blood and put it in a centrifuge, it spins around very quickly with the bottom parts of the test tubes kind of pointed outward. The heavy particles will settle out of solution, like the red blood cells. We call these the formed elements. And so you can see these layers. Up at the top is the plasma, which is the liquid portion of blood. Now we're up to chemical bonds, and I do want you to know 4 types of chemical bonds and be able to understand those. We're going to talk about 4. What is a chemical bond? It's actually the energy relationships between the electrons of reacting atoms. Electrons occupy up to 7 electron shells. We call these energy levels around the nucleus. You may have learned about electrons that travel in orbitals, which has to do with the shape that is outlined by the route that those electrons travel, such as a spherical orbital, and then there's actually 3 dumbbell-shaped orbitals that go in the 3 axes, X, Y, and Z. But just keep in mind that we are going to be talking about a simpler representation. We call it the Bohr model, where we're going to look at these shells, okay? So the first shell around the atomic nucleus is actually the innermost shell. And then as we go outward with progressive energy shells, we're just going to draw them like in a circle. So whatever that, depending on the particular atom, it's going to always have an outermost shell, and depending on the number of electrons in that outer shell, we call that the valence shell. Those electrons have the most potential energy, and those are the electrons that will be chemically reactive with other atoms. The very first shell holds up to 2 electrons, and that from then on, as we go progressively out, each shell will hold up to 8 electrons, and that, of course, is called the octet rule. Chemically inert elements. Now there are some elements that are very stable and unreactive and will not engage in chemical bonding because their valence shell, that outermost shell, is fully occupied. We call these actually the noble gases. You can see them over on the far right. And here are some examples of chemically inert elements. Remember, the outermost energy level, or the valence shell, will be complete. And so they're very happy. Okay, this is called helium. And remember, the atomic number for helium is 2. There are 2 protons in here. Each of these helium atoms has a couple of neutrons. But what we're really concerned with is how many electrons and where are they. You can see there's 2 electrons, and they both reside, of course, on this innermost shell. Now, here's another one. This is quite a bit larger. Neon, the atomic number is 10, so there's 10 protons and 10 electrons in the neutral state. So let's go ahead and count these electrons. There's 2 here, 1, 2 in the first shell, and then we have 1, 2, 3, 4, 5, 6, 7, and 8. And that fulfills that octet rule. It's going to be this valence shell, the outermost shell, is complete. So that's why these atoms tend not to interact with other atoms. Now, chemically reactive elements have a valence shell that is not full. They will gain, lose, or share electrons, in other words, form chemical bonds with other atoms in order to achieve stability by filling that valence shell. And here's some examples. For hydrogen, this one only needs that first shell, but this first shell, in order to be complete, would need 2 electrons. Hydrogen only has 1, and so it's a very reactive element. Here's carbon. Carbon also will form chemical bonds. It's chemically reactive because its valence shell, remember, the octet rule, it should have 8, and there's only 4. And so it has a particular strategy for how it will achieve a full valence shell. And what it does is it'll actually form 4 covalent bonds with other atoms. That's why carbon is a great atom with which we form large molecules that are often big complex structures where carbon atoms will join to other carbon atoms and other atoms will then join to that. This is oxygen. Oxygen has that first inner shell too, and then there are 6 in the second shell out because oxygen atomic number is 8. So you see 1, 2, 3, 4, 5, 6, 7, 8. So in order to have the full valence shell, the oxygen atom will be sharing 2 pairs of electrons. Here's sodium. Now sodium has a different way to achieve a complete valence shell. Actually, its atomic number is 11, so you see the 2 here on the inner shell, 8 on the second shell, and that makes 10, and we have 1 little electron out in this third shell out. What it will do is it will actually lose that electron to another atom, and then it will have a complete valence shell because the second shell becomes its outermost shell now. That creates a situation, though, that we will see in a minute. Once that sodium atom gives up an electron, it's going to end up with a positive charge. So let's go talk about the types of chemical bonds. 1, ionic bond. 2, covalent bonds. This is actually a category because there are 2 types of covalent bonds. Nonpolar covalent bonds, which have no charged regions. Remember, different charges on a molecule would make opposite poles, like a positive side and a negative side. So nonpolar covalent bonds result in a molecule that has no charged regions on it. A polar covalent bond, that molecule will actually have charged regions. And then actually the 4th type of chemical bond now will be a hydrogen bond. So we actually have 1, 2, 3, 4 types of chemical bonds. Typically, the covalent bonds are put in one category, though, and you're going to see the difference between nonpolar and polar covalent bonds in just a minute. Let's start with ionic bonds. An ion results when an atom gains or loses an electron or electrons. As a result of that, it becomes charged. If it gains an electron, it will have a net negative charge. If it loses an electron, remember electrons are negatively charged, if it loses an electron, that particle will now have a positive charge. So the transfer of a valence shell electron from one atom to another will result in an anion, and that would be the atom that gains the electron. It's going to end up with a negative charge, and then a cation. A cation would be the atom that has lost an electron, and it will end up having a positive charge. The attraction now of opposite charges, that's what's going to form an ionic bond. Don't forget, opposites attract. So this is a perfect example of an ionic bond. You can see with sodium chloride. Sodium, which is 11 on the periodic table of the elements, because its atomic number is 11, there's actually 1 electron in its valence shell, and so it's often going to interact with chlorine. The chlorine atom, its atomic number is 17, and so we have the 2 and 8 more. There's 10 electrons in these first 2 shells, and in this third shell out there are 7. 2, 4, 6, 7. The easiest way for that chlorine atom to achieve a complete valence shell is to take an electron, and it often will just accept that electron that sodium gave up. So what this results in is a sodium ion, Na+, and a chloride ion, Cl-. After the electron transfer, the oppositely charged ions are formed are going to be attracting each other. You can see here with sodium, there are still, of course, 11 protons in the nucleus. They don't have them drawn in, but take my word for it, there are 11 protons and only 10 electrons. Therefore, it has a net charge of plus. The chloride ion, which has 17 protons, now has 18 electrons, so it ends up with a negative charge. Ionic compounds are usually salts. When dry, they will form crystals. This is illustrating a table salt, sodium chloride crystal, and you can see this is from when large numbers of sodium ion and chloride ions come together, and they stick very tightly together to form a salt crystal. Here is the yellow ball representing the sodium ion, the cation, remember it's a cation, and the anion, chloride ion right there. Okay, covalent bonds. When atoms share one or more pairs of valence shell electrons, this is called a covalent bond. They are sharing. This allows each atom to fill its valence shell at least part of the time. Keep in mind, electrons are very quick. They're often spinning around various atomic nuclei, and they are hard to get a handle on. So we're going to take a look at the formation of some covalent bonds right here. In figure 2.7a, this is showing you a carbon atom, and remember it likes to make 4 covalent bonds in order to complete its valence shell, because each atom involved with the covalent bond will be able to count each of the electrons that are shared in order to fill their valence shell. So 4 hydrogen atoms and a carbon atom, when they join together, the carbon atom, remember it likes to have 8 electrons in its valence shell. That makes stability. So it can count all of these electrons. 1, 2, 3, 4, my arrow disappeared, 5, 6, 7, 8. So this carbon atom has a complete valence shell. How about the hydrogen atoms? Well, remember, it just has that inner shell. It is complete when there are 2 electrons. So this hydrogen atom can count this pair 1, 2. So can this one 1, 2, this one 1, 2, and this one a 1, 2. So when we draw the structural formula, it will look somewhat like this, and you've probably seen structural formulas before. This is methane, okay, and you can see the carbon atom right here with the 4 hydrogen atoms around that carbon atom. There's also some molecules that are formed with 2 of the same type of atom. This is showing you the formation of oxygen gas, O2. Oxygen, it has actually atomic number of 8. So remember, you've got your 2 electrons on the first shell, and now we have 6 in the second shell. In order for that valence shell to be complete, it needs to have 8 in that valence shell. So for each of the oxygen atoms, when they will form 2 pairs of electrons with each other. So this oxygen atom can count its 6 electrons in this shell, and then 7, 8. And so can this oxygen atom. You've got its original 6, and then it can count these electrons as well. When you share 2 pairs of electrons, that's called a double bond. And so here is the structural formula that shows the double bond represented with the 2 oxygen atoms with 2 lines between them. Nitrogen gas has a triple bond, so this is a very strong bond, and actually nitrogen gas fills about 78% of our air in our atmosphere. So you can see 2 nitrogen atoms. This nitrogen was used before as an example. Remember, the atomic number is 7. So that means there are 5 electrons in its valence shell. There's 5 there and 5 there. When these 2 nitrogen atoms come together, it can count the electron also of the other one with these electron sharing these pairs of electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. And that one now has a complete valence shell. Here's this nitrogen atom that has 1, 2, 3, 4, 5, 6, 7, 8. This is drawn structurally with 3 lines between the nitrogen atoms, and that is a triple bond. Okay, so nonpolar covalent bonds. The bonding covalent bonds that you just saw in the previous examples are nonpolar covalent bonds. And so there's other ones too. This is when electron pairs are shared equally. The electrons are shared equally between the 2 atoms. It produces an electrically balanced nonpolar molecule. And there's another example that they're going to show you, and this is CO2, carbon dioxide. Carbon dioxide and water molecules will have different shape. You'll see what the water molecule looks like in the next example. But here is carbon dioxide. The gray is the carbon atom, and then the red is representing oxygen atoms. This is called a space-filling model. So these are linear molecules. The electron pairs are shared equally, and it's actually, remember, carbon atom likes to form 4 covalent bonds. Each of those bonds does not have to be to a different atom. You can have a double bond from carbon to oxygen atom here, and another double bond to this oxygen atom, and that, of course, makes your 4 covalent bonds. Now, polar covalent bonds are an entirely different story. They are sharing pairs of electrons, but these molecules are formed when the electron pairs are shared unequally. So it produces a polar molecule. That means one side of the molecule will have a positive charge to it, and the other side will have a negative charge to it. And the example is H2O, water. And you can see how it's kind of bent. So you can see this V-shaped water molecule. It actually has two poles of charge. And this is not a really strong negative or positive charge, such as with an ion, but this has a slight negative charge, slight positive charge. And slight is with this Greek letter delta. It looks like a lowercase fancy d. And this is slightly negative on this side where you have the oxygen atom, and then toward the hydrogen atoms you have the slight positive charge. Now if you think about it, this oxygen is quite a large molecule, and it will kind of hoard the electrons over toward itself. The electrons will spend more time over here, and that's why this side of that water molecule has a slightly negative charge to it. The hydrogen atoms are so tiny, they're basically a proton and an electron. So but those electrons are going to be drawn more closely here to the oxygen, so therefore the hydrogen ends of this water molecule will have a slight positive charge. This is really important because when these molecules are floating around together, there will be some attraction between the positive sides and the negative sides. And there's other things that can happen with this polar covalent bond. When we talk about water, you will see some of the principles of water, why water is so important, has to do with this polar covalent bond. Here's the structural formula: an oxygen atom here and the two hydrogens. And that is the end of Part A. I am going to be talking about hydrogen bonds in Part B. Have a wonderful day.